x mu dot del k of eta mu delta x k plus this term, okay, and let me call this as T1, this as T2 plus T2. Now in this term, what I want to do is, I want to, in this term, x mu dot this, yes, I want to interchange k with mu and mu with k. Why can I do it? Because they are dummy indices. So I do it in two steps. First I replace mu by k, and I replace k by mu. Okay, so I can do that, and therefore this would be 1/2 d tau, and xk dot x nu dot times del mu eta k nu times delta x. Okay, so this is what I have done. I have rewritten the term, this term as this. Okay, T1 I have rewritten as this, plus this term, which gave me another two terms, and these terms were 1/2 d tau minus twice eta mu x double dot mu delta x mu minus twice x mu dot xk dot del k eta mu times del x mu. Okay, so this is my entire result. Now I can sum up all of them into 1/2, or I don't even need to do that. Okay, 1/2 d tau into delta x mu into minus twice x dot mu times eta mu minus twice del k eta mu times xk dot x mu dot plus del mu eta k mu times xk dot x mu. So in principle, what happens, this is a result of our variation of the action, and our metric eta mu nu is just a general metric in the general background, which means it's dependent on the x mu. Okay, and so it's a non-flat metric, and now this delta x mu is completely arbitrary, and so if you like, you can write the delta s as before, delta x mu of tau prime of tau. This would give me 1/2 d tau delta tau minus tau prime into this entire bracket. Okay, Yes, and because this would be non-zero, and therefore this would be 0. And this, if you check back with my earlier calculation for the Nambu-Goto action, then these were the 3 terms precisely, where we again break one term into another 2 terms, and I mean from here onwards the steps, second half of the derivation that we had in the Nambu-Goto action are just the same steps. And so that means I could write this as I could summarize this as minus 2x dot mu eta mu minus del k eta mu times xk dot x mu dot minus del k of eta mu xk dot x mu dot plus delta mu eta k mu times xk dot x mu dot. And this is then alpha plus alpha kl xk dot xl dot so this, it does look little bit complicated, but nevertheless it's worthwhile to do this exercise. Okay, I am sure that because this particular equation is the main essence of the general theory of relativity. The general relativity says that the motion of an object is determined purely by the geometry of the space-time. Yes, and so it does not depend on mass, it depends only on the geometry of space-time. And this is the this is exactly this Christoffel symbol, which is determined only by the geometry of the space-time, because its definition, as you see mathematically, I always try to see mathematics coupled with concepts, and you will see that this is defined in terms of the derivatives of the metric tensor. Metric tensor defines the geometry of the space-time, and so this Christoffel symbol defines the geometry of the space-time, and here you have nothing more. And these two, this equation you can look back into our earlier calculation on Nambu-Goto action. You will find this precisely the same. So from here onwards, the steps are just common. After this, the steps are just common. Okay? All right. So with this, if you like, then I could proceed little bit further for the generalization of our considerations that we have made so far. Okay. So our aim is then to describe not only zero-dimensional relativistic point particles, but we want to describe relativistic strings. And strings, so there is one extra space dimension. Okay, so we will have if you would, when you say, then I would remove this, but in the meantime maybe I could write here or if you like I can wait for some time.
It's fine.
It's fine? It's fine. So I can remove this all? All right. As you will see here, that I have not made any special case out of this. So it's a most general derivation. And what happens here, you will see now that this is nothing but string theory. Right now it's for a zero-dimensional object, but the similar identical things would hold true for a string, 0 plus 1 dimension, one time and one space dimensional objects. And you will see that from string theory we can derive general relativity. That is the main idea, that is the main concept behind it. Why we have taken this exercise twice, little bit involved, once for Namagoto, once for Polyakov, because these are the two kinds of actions that we encounter in string theory. And you can derive general relativity from string theory. Okay? So the two are consistent. This is the main result. And in fact, the mathematics is not difficult, it's only tricky. Now, after this, once again, life would start looking much simpler. Let me now generalize this case. Let me not talk mathematics at all. We talk some physics, proper physics. And what I suggest is that we want to talk about strings. And they are